we present SceneRF Self-Supervised Monocular 3D Scene Reconstruction with Radiance views. From a single input image, we want to predict the 3D scene geometry with only 2D supervision. We build upon pixel nerve that represent 3D scene using nerve condition on input image. This allows it to be able to generalize to novel input views. Here is our method. So we first propose a spherical U-net that can hallucinate the feature outside the field view. We then propose the PSR module that can approximate the multi-rise distribution with few points along a long rise. Then we propose to explicitly optimize the depth output from the nerve by minimizing the photometric reprojection loss from the self-supervised depth literatures. And this allows us to have a better depth map that can be used for better scene reconstruction. So next, we would like to present the spherical U-net. So given an image with original field views. So if points lie inside the field view, then we can sample the point feature directly from the image. However, if it lies outside, then we cannot get the feature for the points. One naive solution is to enlarge the image and convolute on the larger support. However, this poses several problems like wide angle distortion or limited field view increase. Our solution is to perform convolution on the spherical domain. Our idea is to divide the field views into segments with equal angles. Then we compute the pixel to angle mappings. And then the segment features is the average feature of the corresponding pixel. And then we can repeat this on a multiple scale to create the spherical U-net. And next, we'd like to present the probabilistic right sampling PSR that can approximate the multimodal right distribution, which is the case in our setting due to the high ambiguities of the monocular setup. In contrast, in the literature, most of the methods focus on unimodal right distribution. So given a rise, we first sample a set of uniform points, so a blue dot here. For each point, we predict a Gaussian, which contain a mean and a standard deviation. We then sample from the Gaussians a set of yellow points and also another set of uniform green points that encourage the right exploration and also avoid this Gaussian falling into the local minima. We then pass them through a NEP MLP to predict the density, which are then used to estimate another set of Gaussian using the Pearson algorithm. We then minimize the KL divergence between the corresponding Gaussians, and we also encourage one Gaussian to match the depth of the rays. So given the learner, we now query the novel view and depth at the novel positions, which is we sample along an imaginary straight path from the input views with equal angle also to the left and to the right. Then the 3D view can be computed by fusing the depth and the views. And next, we'd like to show some qualitative results. First, on novel depth view synthesis. So given an RGB input views, we synthesize novel depth views along an imaginary path. We have our method on top and the three baselines. We can see that we predict much better depth than the baseline. And we also show some result on the novel view, which is secondary task. And on another scene. Next, we would like to show some result on 3D scene reconstruction. So we have the input image on the left and the 3D scene on the right. And also on bundle fusion. We also show result on the sequence of simplicity compared to pixel nerve, which is a method that we build upon. That is the end of my video. Thank you very much for watching and don't hesitate to check out my past works.